So I'm the director of the Huawei Advanced Wireless Technology Lab in Paris. So this lab is, let's say, working on the future 6G, and essentially the physical layer and let's say the lower layers. And this is because, in fact, we were starting to work on 6G, that this theme of semantic information or semantic communication appeared to us. And so we had a deep dive on that. And finally, we had some conclusions that I will show you. So this talk is the first talk of a series of 2 talks on semantic information. So the first one is based essentially on, maybe a historical approach, and also on some simple examples that will show you what it is. And the second part that I will give next week will be essentially about semantic spaces, which are, in fact, let's say, the equivalent to Shannon's information measure for the traditional information theory. So here we are at the level of the semantic information theory, something that has never really attracted so much attention until nowadays. And because nowadays we wanted to make agents, intelligent agents, communicate between them, all together. And also because we have this notion of, because it is related to this native AI part of what should be the future 6G. This is why it's time to study, to do research on this theme of semantic information. And of course, beyond 6G, it's something that I'm sure will be very important also for many other topics of interest. So let's start with a simple question. The question is simple. The answers are quite complicated to tell you. So what is information? Okay, let's try to go back, in fact, to the most famous notion of information. And before, let's have a look at what is called goal-oriented communication. So it's a notion that pops up from time to time, let's say, among researchers who are trying to really do a semantic communication, but it's a small part of what semantic communication should be. So, in fact, in this case, I have a very simple example. So suppose that you have an image here that you want to infer, and you want to do some analysis, and you just want to know if the image represents a lion or not. That's it. So you use, for example, deep learning for doing that. In fact, what you will have at the output of here, the neural network, will be this thing. A proposition formulated in a given language, which is X is of the type lions. So X is the image, of course. And you need to say if it is true or false. Oops, sorry. That's it. This is the only thing you have to do, right? So, of course, you train your network with many images of lions and non-lions, of course, and then you hope that you will have a network that will work properly. Okay. So, in the traditional setting, suppose that you want to transmit this notion in traditional setting, what would you do? You would, in fact, transmit the full image, maybe encoded using JPEG or something, any traditional image compression you want. And then, in fact, the receiver will reconstruct it according to some distortion criterion, right? Because it's exactly how this kind of source coding works. Okay. But of course, in order to transmit this full image, you will have used quite a lot of resource. And don't forget, the only thing you wanted to know is if there is a lion or not. You don't want to know if exactly how the lion is. You don't want to know that there is a baboon with a stick, with a wooden stick. I mean, you just want to know if there is a lion or not. That's it. So there is a naive approach where you just transmit one bit. After all, you just want to know if there is a lion or not. So it's a binary. It's just a binary decision to be taken. So, but okay, is it enough? Of course not. Because if the receiver receives one bit that says there is a lion or not, the problem is that the receiver should have an idea of what is a lion, in fact, because, of course, for us, we know exactly what it is, but maybe the receiver has no idea of what is this concept, lion. And it means that it doesn't know, a priori, its meaning, so it's semantics, right? And of course, the semantics as well, in this example, needs to be communicated at least once. So that means that how can it be done? It can be done by, I don't know, by using transfer learning. You can transfer all weights of the trained network, maybe, but of course it can be very heavy. And probably we don't know if we are close or far away of the limits of the limits that can be defined about semantics of lion. So, and that means that we need probably to understand more and much better what is this notion of semantic information. All right. So let's go back to this now. So, of course, you know who is the man on the right. So it's Claude Shannon. He's doing what he was doing during the second part of his life. Juggling was one of his patients. And, you know, of course, this fantastic monograph, A Mathematical Theory of Communication, where he founded the area of information theory. But of course, we're not interested in this. We're not interested in the probabilistic approach now. We're interested in something different, in something else. So we are in fact interested in a kind of post-Shannon information theory. Let's say that 3 or 4 years after he published his monograph, A Mathematical Theory of Communication, then in fact he made some corrections in this monograph and included it in a little bit bigger book that he wrote with Warren Weaver. And Warren Weaver mainly, in fact, wrote an introduction and a conclusion. This is how he introduced the famous Shannon's mathematical theory of communication. So for him, it seems reasonable to ask serially, how accurately can the symbols of communication be transmitted? So the famous level A, what we call the technical problem. So it is exactly what Shannon solved. And then there are 2 other levels, level B and level C. How precisely do the transmitted symbols convey the desired meaning, so the semantic problem, and how effectively does the received meaning affect conduct in the desired way, the effectiveness problem. So as you can see here, I mean, now the bits are not all equivalent, because in the first case, let's say that if the bits have the same probability, there is nothing that can distinguish one bit from the other one. But now they convey meaning. So of course, all these sequences of bits do not have the same meaning. So, and we need to try to understand it much, much better, right? And also there is a question now that can ask, is it possible to get a theory of semantic information of the same type as Shannon's one? It means, you know, having first some theoretical limits about what we don't know for now, because even without computing any limit, nobody knows exactly what these limits could represent now regarding, let's say, a theory of semantic communication. So Then you have some limits to compute, and you know that you cannot go beyond these limits in terms of what, I don't know. And then from this thing, you need, in fact, to design a coding scheme. It can be, maybe there is an equivalent to source coding, to chunk coding. I don't know for now, and what it can represent in terms of semantic computation. And so all these things have to be defined. And so it's a huge, huge, huge work that will probably, if we can achieve some results, some preliminary results, many, many people can have research work during decades with this. So let's go now to something which now is more perspective. Let's say it is the consequence of discussions between myself and my colleague Daniel Benquin, with whom I did this work. So what should be a theory of information? So this is very important to answer this question, because I mean, if we say a theory of information, I mean, everybody thinks of Shannon, right? But if we want to do something different because of this famous semantic communication problem, so how should we proceed? So we need to understand what can be a theory of information, any theory of information. Okay. So our postulate is that any theory of information is a theory of ambiguity. I will be more precise in the slides and the other ones that will follow. Okay, in order to, let's say, make the recipe of Shannon's information theory, we need a couple of ingredients. We need probability, of course. We need random variables as well. We need a measure of ambiguity, which in this case will be the entropy. Why is it a measure of ambiguity? Suppose that you consider a random variable that is that can take so x that can take a finite number of values. All right. We know in this case that the entropy will be maximized when the distribution of probability of x will be uniform. What does it mean? It means that for each value that x can take, you have exactly the same probability. Because you have the same probability, you are unable to distinguish, at least in a Bayesian way, any of these values. All right? So, and this is what in Shannon theory ambiguity means. But now you can, let's say, relax the ambiguity or add some more ambiguity by using, in fact, this fundamental equation, which is, I didn't put any mutual information because you can always, let's say, recover the mutual information just by using entropies. So for me, you just need for now, the entropy is enough, right? So, and this fundamental equation is very important because you have a new term, let's say a new expression that pops up, which is h of y conditioned to x. So the conditioning process is the process that will, let's say, remove at least partially some ambiguity. Okay, so we have a process to remove at least partially some ambiguity. Okay, so now suppose we are considering another type of information theory. Let's call it an alien information theory. Okay, so in this case, you need to have the same thing. That means, let's say, something equivalent to the probability that I will call T. So you will see later why I call it T. The equivalent of random variable, which I will call P, and we will see afterwards why it is called P. A measure of ambiguity, okay? In the Shannon's case, it was a number, let's say, the entropy. In our case, I mean, if you consider semantic information theory, we will see that the number is not enough. We need something else. And then finally, a fundamental equation that show you how to go towards more or less ambiguity. All right? Okay, in this case, what should we do to understand the better? In fact, we have to go back to Galois, because you have to know Galois was the first one to establish a theory of ambiguity. It was not a theory of information. I mean, he didn't call it this way. But already, you know, the day before he died, he sent a letter. So for those who don't know, he died at the age of 21, very young. And he sent to probably his best friend, Antoine Chevalier, a letter saying that he was, in fact, founding a theory of ambiguity. This is something, it is exactly his words. So let's go back to Galois theory. So even if you don't know it, you can understand through some examples how it works. So suppose that you have this problem to solve. So you have a polynomial p of degree n with rational coefficients, all right? And this polynomial is irreducible, all right, in Q. That means you cannot factor this polynomial by using rational numbers, right? What do we know? In fact, there is, in this case, if you call theta a root of this polynomial, which will not be a rational number, of course, and then you define Q of theta as being the minimal field that contains both Q and theta, then in this case, the language we are using is enough to name all roots of P. That means, in fact, what happens is that once you say one of the roots is theta, you call it theta, so it is a word that you have in your language now. In this case, you can see that all other roots can be expressed as polynomials in theta. That means that knowing theta, the rational numbers, what the addition is, and what the multiplication is, you are able, in fact, to name precisely all roots of P. So it means that you have basically no ambiguity. You can distinguish each of these Ri. Okay, I have an example, a very simple example. Suppose that you have this polynomial, P of x, x4 minus x3 minus 4x2 plus 4x plus 1. So in this case, you call theta one of the roots of this polynomial, and then the set of roots is theta, theta 2 minus 2, theta 3 minus 4, theta, etc. So that means that you can exactly name all roots of this polynomial. Okay? So the language is enough to remove all the ambiguity. Now suppose that in your language, there is something that you don't have. You don't have the letter theta. In this case, basically, you just have the rational numbers, the addition, and the multiplication. That's it. So, of course, in this case, the language is insufficient to name any root of this polynomial. Basically, you have a total ambiguity as, in fact, indeed, we cannot distinguish any of these roots because we cannot even name them, right? The only thing we know is that we have n roots, but they are in some other field than Q. It's something above Q, right? So, is it the end of the story? In fact, not. No, sorry. Because Galois found that there is a group, so a group of permutation, which acts on the set of roots that send one root to another one, etc. And this group give some structure to this set of roots. Even if you cannot name them, you know how they can be exchanged. And this group, we will see it later on, give to this set a kind of shape. And this shape will be, in this case, the information related to the ambiguity that we have here. So
Jean-Claude, we lost the audio from your side.
Oh, sorry. Is it better now? Can you hear me?
Still, we cannot hear you.
Oh, sorry. And now, is it fine?
No, there is.
Oh, I don't know. It's coming back?
Yeah, it works.
Okay, sorry.
Yeah.
When did you lose me?
When you were saying that the Galois group contains all the permutation of the
Okay, good. So there is this structure of the Galois group which depends on the polynomial. If you change the polynomial, you can change the group or not. Yeah. So if you consider the same example, x4 minus x3, etc., then we can compute the Galois group. It's not an easy calculation, but it's doable. And it shows that the Galois group for this polynomial is the cyclic group C4 with the 4 elements. So that means that it is as if you were considering the addition of integers modulo 4. This is okay. It's a detail because it doesn't. Yeah. So, and knowing the Galois group says many things. Okay, even if you cannot name the roots. So in this case, you have a language which is less rich than when you had theta. It is less rich, probably, but even if it is less rich, you can say many interesting things. And you will see that, in fact, artificial intelligence works exactly in the same way. So you can, of course, be finer than what I showed you. Suppose that now between Q and Q of theta, you add something else. So you have a new symbol, which is phi. So you enrich your language. Phi is a root of this polynomial, x2 minus x minus 1. And in fact, phi is also an element of Q of theta, right? So it is the famous golden ratio. So Enrico, told you about our discovery on the golden code, which was using this golden ratio. So finally, the history starts again and again the same way. So in this language associated to Q of I, so in this case you have phi. You don't know the symbol theta. You don't know it, but you have phi in this language. So now you are in between. The set of roots now are non-distinguishable pairwise. So you have basically two pairs. One of them is theta and theta 3 minus 4 theta plus 1. You cannot distinguish these pairs because to distinguish them, you have to use theta, right? But the minimal polynomial, that means the polynomial with these two roots, will be this one, x2 minus phi x plus phi minus 2. That means that, of course, you have the right to use phi. So, and you use it. So in this case, because you can use phi, then you can split the set of roots into these two pairs. And then you have another pair of roots. You cannot distinguish the roots of the same pair, the same set, but you can distinguish the two sets of roots, so the two pairs of roots. So, and both, so these two pairs have a Galois group, which is C2. So basically it's the 0, 1 with the binary addition acting on them. All right, so exactly the same thing. So let's summarize this. You have a tower of fields, Q of phi, Q of theta. So at the bottom, you don't know anything. The only language that you have is the one using rational numbers, addition and multiplication. Then you enrich your language with phi, and you go towards less ambiguity. And then you enrich it with theta, and you go towards even less ambiguity. So you see, but so you have either you have less and less ambiguity, and you have basically nothing acting on this ambiguity, or you have more and more ambiguity, and you have, in this case, a group acting on this set of roots that add some structure and that you can, of course, enjoy for doing many other things. Okay, so this is the conclusion of what Galois theory can bring to our notion of information. I will show you some other examples, much more related. to the problem of AI later. If you want to know more about this, there is a very nice presentation of Alain Cohn, which is entitled Évariste Galois et la théorie de l'ambiguïté. So I encourage you to have a look at his slides, so they're in this link, because it's very well written and it's very nice. Okay, so after Galois, we have two other characters to meet, let's say. And these two characters are Carnap on one side and Bar Hillel on the other side. So, in fact, basically, they have, so 4 years after Shannon, they wrote a paper about, let's say, a mathematical theory of semantic communication, let's say. But so basically, they have been the first ones to publish something about semantic communication. And I think that since then, there has been almost basically no significant progress. So this paper is from 1952, so you can see it was published 70 years ago, and basically no progress. So first of all, we need to analyze what is inside this paper, because it's very important, very interesting. My opinion about this is that they didn't have at that time the basic mathematical tools that would have allowed them to go much beyond what they have done. Because at this time in mathematics, in fact, all mathematics were based on the set theory, right? And you will see that their vision is a pure set theoretic vision. And you will see also that the notion of semantic information that they derived is not enough because it is based on set theory. And I will show you on an example, at least this time. Next week, it will be a little bit more technical and more general. But at least this time, I will show you how to go beyond the set theoretic aspect. So, and in fact, for doing that, we will use some math that have been invented, let's say, after Carnap and Bar Hillel wrote their paper. So that's why it's they couldn't, of course, know it. So what is the background? So this is, in fact, the header of their paper, let's see, the title page, an outline of a theory of semantic information. So you see. So, in fact, what did they do in this paper? So basically, they introduced a propositional Boolean language. Because, of course, if you speak of semantics, I mean, everybody will tell you semantics is related to language. I mean, and it's true in the everyday life, it's true in linguistics, it's true in philosophy, but it is even true in mathematics, and it's even true on these technical aspects that I will show you. So you need a language. In their case, it's a Boolean propositional language, right? I can be more precise. They have this language L and pi. So it's a kind of language which is, let's say, subject, attributes. That's it. So a subject is blah, 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 or blah, 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 and blah, 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 etc. Something like that. So they have n subjects. All of these subjects can have pi different attributes. And each attribute can take, respectively, pi I possible values, all right? Then they describe what they called state descriptions. So state descriptions can be seen basically as atoms of this language. So it means that you say for each subject, what are the values of all possible attributes, all right? So it's super precise. If I go back to this famous theory of ambiguity, it is the state descriptions correspond to no ambiguity at all, because you precise for all subjects what are the values of all possible attributes. But then, of course, from these state descriptions, you can form many more propositions by considering predicates that use the disjunctions or negations. And of course, if you want to be a little bit more complex, you can use also conjunctions. I mean, okay. So now, as this language is Boolean and propositional, it means that, in fact, the number of state descriptions will be chi, which is the product of all pi I, to the power n, which is the number of subjects, okay? And so that means that if you use, for example, a set model, the state descriptions can be seen as the elements of a big set, all right? And then the set of all propositions that can be formed by using these state descriptions is just the subsets of this big set. So you have basically a total of 2 to the power chi subsets, so a number of 2 to the power chi possible propositions, all right? But first remark, suppose that you have this very simple case where you have 4 subjects. The total number of attributes is 2. So the first attribute can take 3 possible values, and the second one 2 possible values. Just compute the total number of propositions. It will be much bigger than the total number of atoms in the visible universe. So just to give you the big problem that we are facing, okay? With this super simple language, it's hard to imagine something simpler. Already, the number of propositions is so huge that you cannot even imagine how big it can be, right? So now, if we complexify a little bit in this language, of course, it becomes impossible to do anything, right? So why is the case? In fact, these state descriptions can be seen as a kind of machine code. So that means something that can I mean, you can do basically everything with this, but you are unable to use them, right? Because for us, I mean, there is no true meaning. It's something which describes precisely all elements. It is as if you were considering everything surrounding you by considering each possible atom of what you are seeing, what you are listening to, what you are, you know. So of course, it's not the way our brain is working, definitely not, all right? So we need to go beyond that aspect to understand really. So just to finish with Carnap and Bar Hillel understanding of the semantic information. So they introduced, in fact, these things. So first of all, they introduced an axiomatic notion of set-valued information, which they call in of P, where P is a proposition in the Carnap and Bar Hillel language, all right? So that means that to each proposition P, which can be a state description or not, I mean, they associate a kind of a set, let's say, which they call an information measure. So already you can see that in Carnap and Bar Hillel, you do not measure the information by using a number. You use a set to measure the information. It has a very, very, very big impact, because in our understanding of semantic information, we will even generalize this notion of set-valued measure of information, all right? Then, in fact, they proposed, so an axiomatic notion, that means that the in of P, they don't define what it is, but exactly, they don't construct it, but they say it has to satisfy axiom A, axiom B, axiom C, etc. Okay? And then they propose a constructive notion, which they call the content associated to any proposition. And then maybe they were regretting to use a set value the functions, because, I mean, as you know, everybody in channel information theory, for example, is using numbers to measure information. So they, instead of using a capital I-N, they use a small I-N, which is, let's say, a numerical information that they can derive from the set valued information, and same for the content. All right. Okay. What you have to know is that all these notions are related to one thing: how P is written as a disjunction of state descriptions. That means you have P can be written as one state description, or another state description, or another state description, etc. Right? So basically, this notion of semantic information introduced by Carnap and Bar Hillel is related to the number of state descriptions you need to describe your proposition. All right. So that means that this notion of semantic information just depends on how many state description you need to describe your proposition. So, of course, it is more or less the only kind of how to say. It is the only kind of semantics that you can derive from a set theoretic notion. And of course, it doesn't correspond at all to the way we as human beings, our brain also, is seeing the meaning. All right. So that means that we need to go beyond this notion of set theoretic information measure. All right. Let's have a look at some interesting connection with machine learning. In this case, it can be, for example, DML. Suppose we have here, so we want to analyze a picture. So here, so you can see it's a pixelized picture, pixelized image, and it's made on purpose, of course, which basically represents a sunflower. And so you can see, in fact, this image as, in fact, by using a Carnap and Bar Hillel language. So what are the subjects? The subjects are just the pixels of this image. The attributes, you have three attributes, which are basically the primary colors, red, green, blue. And the values that can be taken by these three attributes are just the 256 levels of gray of each color, right? So basically, what is a state description? In this case, a state description is just one single image. You can describe one single image by saying the red part of pixel 1,1 has values blah blah blah, and the green part of pixel 1,1 has value blah blah blah, and the blue part of pixel 1,1 has value blah blah, and the red part of pixel 1,2 has value blah blah, etc. And you do that for all pixels of the image. Of course, you will obtain, let's say, you will obtain a state description which is many kilometers long, because I mean, it can be, of course, dramatically complex to write it. But it's not the end of the story, because when you want to really analyze this image, for example, if you want to know if there is a flower in this image, then the problem will be even more complicated. So suppose that you use now DNN for classification task, which is to recognize if this image represents a flower. Then you can, of course, express the output, so by using an output language, which is a huge disjunction of state descriptions in order to characterize the semantics of the flower, what the flower is. So what I mean is that you can say that the flower is this image of flower, or another image of flower, or a third image of flower, or etc. And you can have millions of images of flower, or even more. So you would have a disjunction of millions of state descriptions. So it's, I mean, it's not even a kilometer-long formula, but maybe, I mean, it's completely crazy to write it in this way. Okay. So in this case, it means that you need to change the language. And in this case, you can use a very simple language. Why? What you want to know is just, in this case, so your goal is just to know if the image represents a flower or something else. That's it. So you only remember the picture with the lion. So you just need to answer this question. Is X a flower, or X is a flower? Yes or no? So true or false? That's it. So that means that it's a very simple language with one type, which is the type flower. That's it. So in this case, of course, the set-theoretic information measure of Carnap and Bar Hillel would be, let's say, would correspond to the number of state descriptions that you need to use. So the number of images that with which you need to train your network in order to recognize a flower, probably with an accuracy which is satisfactory enough. All right. So it makes some sense, but of course, you can see that probably you can go beyond that because this is not at all the only thing we can do. What can we do? In fact, we can see here in a DNN rather a kind of Galois theory where you have a maximum ambiguity achieved at the output layer. So the input layer let's say, is connected to the raw image. So it's very precise. You have no ambiguity. You can describe the image pixel by pixel. And at the output, you have a language with just with a vocabulary of one word, flower. So that means that you can just say flower or not, but you are just interested in that. So it's enough. But you cannot say if it is a sunflower, a rose, or something else. You cannot say the color of the flower, the size of the flower, how it smells, or something like that, you know? And so that means that, of course, it means that you will have a language, but what is interesting is that probably you will have some notion of structure. Maybe it's a group, who knows, but in general, it will be something else than a group that will act on this word flower and like the Galois group on the roots of a polynomial and will give it some shape. And what we state, I mean, our statement is that the understanding of a notion is definitely related to something that acts on this notion. Okay, and that will exactly define this notion. Let me be more clear by considering again the Carnap and Bar Hillel language, but not in a set theoretic version. Let's try to go beyond that, and let's see something which is very similar to Galois theory with the action of a group. Okay, so here you can have on the left, let's say an array, which is directly copied from the paper from Carnap and Bar Hillel. So you can recognize three subjects, A, B, and C, two attributes, which are the age and the gender, and for each attribute, you have two possible values. So male, female for the gender, and young, old for the age. All right. So you have to understand that in this example, when I say gender, it doesn't really represent the true notion of gender that we understand. It's just a label without any, let's say, without any semantics, that, I mean, without the semantics we know. Same for the age and same for male versus female or young versus old, all right? That means that all these things are exchangeable. You can permute it because in this semantics, all subjects are equivalent. I mean, there is not A which is more important than B, or which encompasses the notion of B or of C, and same for the genders, or the ages, right? So, and let's have a look, a more precise look at the 4 first rows of this array. So you can see the first row is that A, B, and C are all of them male and young. The second one is that A, B, and C are all male and old, etc. So that means that you can, if you do a disjunction of the 4 first rows of this array, it means that you want to say all subjects have the same attributes. Of course, I use the natural language, I use English. You can use another language that will convey the same semantic information, but this is what I mean, all right? How to formulate the semantics of the semantics information measure of this sentence. Okay. First of all, let's, in fact, we have to say that there exists a Galois group G of the Carnap and Bar Hillel language, which is generated by the permutation of the n subjects. Okay, if you permute the n subjects, because the subjects have all the same importance. I mean, you cannot distinguish A from B from C, all right? So then it means that the group of permutations that act on a set of 3 elements is part of the Galois group of the language that is used there. And then you can do the same for the attributes. So that means that you can permute, for each attribute, you can permute their values, because there is nothing conveying some more importance or something, let's say some semantics precisely because of the reasons that I told you. And also you can permute the attributes themselves that have the same number of possible values. So in this case, they have 2 values. So of course, they have the same number of possible values, so they can be permuted. Of course, if you have attributes that don't have the same number of possible values, they cannot be permuted because they represent 2 different things, right? Okay. Then the group of subject permutation is just the group of permutation of a set of 3 elements. And then for the attributes, in fact, you can arrange them by saying that the 4 pairs of attributes, male, old, male, young, female, old, and female, young, form the vertices of a square. And so the group that acts on this square is just the group of symmetries of the square, which is the dihedral group D4. And it corresponds to, it is generated by the rotations with an angle multiple of pi over 2, and by the symmetries along the vertical and the horizontal axis. All right. So we can say, because the subjects and the attributes are independent, we can say that now the Galois group that is acting on the Carnap and Bar Hillel language is just sigma 3 times D4. So it's a direct product. That means that you can represent each element of this group by a pair. The first component of this pair is in sigma 3, and the second one is D4. In the language of contemporary mathematics, that means beyond what Carnap and Bar Hillel could know, we can say, and it will be more precisely defined in the second talk, that the language L in this case is a presheaf over the group G. And you have to know that the collection of all possible presheafs over the group G is called the Grothendieck Toposes, which in fact justifies the title, but I will not say you more about the toposes this time. We'll see it next week. So you have also 4 different types of orbits, and which will correspond to 4 different sentences. So the type 1 is the type that I showed you before, where all subjects have the same attributes. Okay. In this case, it can be represented this way. And you have the 4 pairs of attributes, like young male, old female, young female. And then your group, initial group, it is as if it was split, into 4 different objects, which are these 4 vertices. And then you have some elements of the initial group send the vertices onto themselves. So it is a subgroup of the initial group called the stabilizer. And the other ones send a pair of attribute to another one. Okay. So this thing, where you have objects here, young male, old male, etc., and arrows between objects, and these arrows are invertible because they come from a group. It's called a groupoid, and it is, I will stop here for today, my presentation. It is one measure of information, in this case, corresponding to the type 1, which is translated into all subjects have the same attributes. So this proposition has an information measure, which is not a number, which is not a set, it's beyond sets. It is what is called a groupoid, and it is what is called also, it's a kind of category. And I will go back to this in a more general way next time. So I will stop here my presentation. Thank you very much.
Thank you, Jean-Claude. I don't know if it was easy for follow, but it was very dense and intense. I don't know if there is any question through the chat or through the question and answer. As Jean-Claude said, this was let's say, the introduction that we will continue next Wednesday with more precise definition and also the mathematical tools that are implied into this theory of semantic information. Yeah, I don't know, is there anyone from the Q&A or the chat? No? Jean-Claude, I had one question, but it was not technical because it's not close to what I actually do normally. But so basically what you are saying is that we are looking at reality with the microscope, whereas we should have a vision that actually is meaningful for what we can see, right? This is
sure, of course, definitely. It's something that I will detail next time. Yeah. Okay. But
so yeah,
it's
just the topic is a tool that will allow us to understand what comes from reality in their meaning.
Yes, in fact, yes. In fact, the idea is, in fact, this can be applied to many types of scenarios, because for now I just, let's say, put in place the it's a basic framework that I needed for next time, right? And so what we have here is how to say, you know that, for example, if you go back to Shannon information theory, so Shannon, as you know, has pushed forward the development of telecommunications and in a way which is fantastic, right? And the problem is that for semantics, for now, we have basically nothing. And so what we need to understand these notions, and especially, for example, if you want to establish a semantic communication, right? The idea is that what do you need to transmit in order to do that? So it's not traditional communication because you need to transmit some knowledge, and also you need to transmit some capability of understanding some notion. For example, as in the very small example that I showed, you want to transmit what is a flower to a receiver, all right? So it's not an easy problem. Okay, you can train in a traditional way a network to recognize a flower by using millions of images of flowers and non-flowers, and then just to transfer the coefficients. But in fact, this is not a good way because you will see later that by doing that, you are very, very, very far away of the limits. That means that you will use a very huge bandwidth to transmit it, right? Because, just to recognize a flower, you need a lot of parameters in your neural network to be trained in order to do that. So first of all, to train your network, you need a lot of data, and then, whatever, you can send either the training data or you can send the weights of your training network. It's a lot. And also this way of learning is, I think you know the famous talks of Benjo, for example, of that topic, is the system one way of learning. There is, even if we know exactly how it works, now there is another way, which is what is called system two. In fact, it's coming from an American psychologist. And this system two is not trained in the same way. It uses languages. It's something that is, to be developed. It's not something that is already developed. It has to be developed still. And what I believe is that, of course, it's the development of such new systems is intimately related to this notion of semantic information. What I mean is that even if I talk of semantic communication, I don't think that the ultimate application of this notion of semantic information will be just to transmit semantics. This will be probably a secondary effect, let's say. What I believe is that the very big thing that could rise from the study of semantic information will rather be the possibility of designing new architectures of, for example, neural networks that will be able to implement this notion. It means be able to reason, be able to generalize, to really generalize, and not like nowadays where the generalization capabilities are very narrow sense, let's say. And all these notions. And in my presentation of next week, all these things will be